Every year, earthquakes and storms threaten to bring skyscrapers crashing down. Yet the world's tallest buildings, rising 100 floors into the sky, stand firm. How is that even possible? Today, we tear open a 100-story skyscraper, layer by layer, to reveal the invisible engineering secrets inside. From the foundation buried deep in bedrock to the golden crown at the very top. This is structural engineering at its most extreme. Let's start from the outside, the skin of the building. This curtain wall, a glass and aluminum curtain wall, is not just decoration. The curtain wall panels are designed to flex, to absorb wind pressure without shattering. During a Category 5 hurricane, wind pressure on a skyscraper facade can exceed 200 kilograms per square meter. That is equivalent to a small car pressing against every single square meter of glass. Now let's strip away the curtain wall and look at the structural skeleton underneath. What you see is a steel and concrete core, the spine of the entire skyscraper. This structural core runs from the basement all the way up to floor 100 without interruption. But before we go up, we need to go down, deep underground. A 100-story skyscraper generates an enormous downward force, sometimes over 300,000 tons pressing into the ground. Engineers solved this problem using deep foundation piles, massive steel and concrete piles driven down to bedrock. These foundation piles can reach 60 to 80 meters below street level, that's 20 stories underground. The foundation piles transfer the weight of the entire skyscraper directly onto solid bedrock below. But there's another problem. The ground itself can liquefy during a powerful earthquake. Soil liquefaction, when the ground behaves like quicksand, is one of the deadliest threats to tall buildings. To counter this, engineers install a reinforced concrete mat foundation, a massive concrete slab connecting all foundation piles together. Now let's rise up through the structural frame, the true skeleton of the skyscraper. A modern skyscraper frame is built from high-strength steel columns, steel beams, and reinforced concrete cores. The steel columns carry the vertical weight, all 300,000 tons pressing straight down. The steel beams transfer horizontal loads, the enormous push of wind from the side. But columns and beams alone cannot stop a building from swaying like a tree in a storm. Engineers add diagonal steel braces, called a braced frame system, to create rigid triangular patterns inside the structure. Triangles are the strongest shape in structural engineering. They cannot be deformed without breaking aside. Many super-tall skyscrapers take this further, using a megaframe system with giant diagonal braces spanning multiple floors at once. Let's talk about wind, the invisible force that engineers fear the most. At the top of a 100-story skyscraper, wind speeds can reach 250 kilometers per hour. This creates a powerful lateral force, a horizontal push trying to topple the entire building sideways. Without resistance, a skyscraper could sway over 1 full meter at the top floor during a major storm. To fight this, engineers test every skyscraper design inside a wind tunnel. Wind tunnel tests reveal how air flows around the building, where dangerous vortex zones form. Vortex shedding, alternating wind vortexes on each side of the building, can cause dangerous rhythmic swaying called resonance. Resonance is when the wind frequency matches the building's natural frequency, amplifying vibrations dangerously. Engineers break resonance by shaping the building with tapered profiles, twisted forms, or corner cuts. The twisted shape of the Shanghai Tower reduces wind load by 24% compared to a flat-sided building of the same size. Now here's where it gets truly fascinating, the secret weapon hidden inside the building's crown. Many super-tall buildings contain a massive steel or concrete ball suspended near the top, called a tune mast damper. The Taipei 101 tune mast damper weighs 660 tons, that is heavier than 100 adult elephants. This tune mast damper hangs on thick steel cables between the 87th and 92nd floors. When wind pushes the building right, the massive tune mast damper swings left, counteracting the sway. The tune mass damper is precisely calibrated, tuned to the exact natural frequency of the building itself. This pendulum mechanism can reduce building sway by up to 40% during a major typhoon or storm. Now let's face the most violent force of all, the earthquake. An earthquake sends seismic waves rippling through the ground, waves that travel faster than a speeding train. When seismic waves hit a skyscraper foundation, they transfer violent horizontal and vertical forces into the structure. The most dangerous earthquake frequency is between 0.1 and 10 Hz, which matches the natural sway frequency of tall buildings. Engineers counter this using base isolation systems, essentially placing the building on giant shock absorbers. A base isolator is a layered rubber and steel pad, called a lead rubber bearing, placed between the foundation and the building structure. When the ground shakes violently, the base isolators absorb and deflect the seismic energy, allowing the building above to move slowly and gently. This reduces the seismic forces transferred into the building by up to 70%. In Japan, engineers go even further, using active mass dampers with computer-controlled hydraulic actuators that react in real time. Sensors across the entire building detect vibration, and the active mass damper system fires within milliseconds to counteract it. At the very heart of every modern skyscraper is a reinforced concrete core, a massive hollow tube of reinforced concrete. This concrete core typically houses the elevators, staircases, and utility shafts, but its real purpose is structural. The reinforced concrete core provides torsional resistance, resisting the twisting force that wind and earthquakes apply to the building. Reinforcing steel bars, called rebar, are woven into a dense cage inside the concrete core walls. The rebar cage gives the concrete tensile strength. Concrete is strong under compression but weak under tension without steel reinforcement. In super tall skyscrapers, high-performance concrete with compressive strength up to 120 megapascals is used, twice as strong as normal concrete. One of the most revolutionary skyscraper engineering innovations is the tube frame system. Invented by engineer Fazlur Rahman Khan in the 1960s, the tube frame system treats the entire building as one giant hollow tube. In a tube frame, closely spaced steel columns around the building perimeter form a rigid hollow tube, like a steel mesh cylinder. This tube frame resists lateral wind forces far more efficiently than interior columns alone could achieve. The Willis Tower in Chicago uses a bundled tube system, 9 interlocked tube frames fused together for maximum strength. Modern skyscrapers are no longer just steel and concrete, they are intelligent living structures. Hundreds of structural health monitoring sensors are embedded throughout the building, measuring stress, vibration, and tilt in real time. Accelerometers detect tiny vibrations, measuring accelerations as small as 1/1000th of a gravity unit. GPS antennas on the roof track the building's top floor position, detecting sway to within a few millimeters. All this sensor data feeds into a central computer system, creating a complete real-time structural health portrait of the skyscraper. Let's look at the materials revolution happening inside today's skyscrapers. Ultra-high-performance concrete, called UHPC, contains steel fibers mixed into the concrete matrix, making it 10 times stronger than normal concrete. High-strength steel grades like S690 can carry enormous loads using far less material, saving weight and cost. Shape memory alloys, metal alloys that return to their original shape after deformation, are now being tested as earthquake-resistant structural connections. Let's see these engineering principles at work in the world's most iconic super-tall skyscrapers. The Burj Khalifa in Dubai, standing 828 meters tall, uses a Y-shaped floor plan with a reinforced concrete core to resist both wind and seismic forces. The Y-shaped cross-section of the Burj Khalifa disrupts vortex formation, reducing wind-induced sway dramatically. The Shanghai Tower uses an innovative double-skin curtain wall, a building within a building, that reduces wind loads and saves enormous energy costs. During the 2011 Tohoku earthquake in Japan, one of the most powerful earthquakes ever recorded, modern super-tall buildings in Tokyo swayed but did not collapse. That is the power of modern structural engineering, buildings that can absorb catastrophic forces and protect every person inside. A 100-story skyscraper is not just a building, it is one of humanity's greatest engineering achievements. From the deep foundation piles anchored to bedrock, to the tuned mass damper pendulum swinging silently at the top, every component works together as a single survival machine. Every skyscraper you see on a city skyline is quietly fighting, every single day, against wind, gravity, and the movement of the Earth itself. If you found this engineering deep dive fascinating, smash the like button and subscribe. New mechanical breakdowns every single week. And comment below, which engineering system surprised you the most?